This is it. My goodness, congratulations. You have made it to the final hypothesis test of the year. And you did most of them in quarantine. This is crazy. I'm so proud of you guys. Hey, we're going to end basically where we've begun. And when I say that, I mean, when we began hypothesis testing, what was the very first assumption that we made? That we were taking independent, random samples. But how do we know if the samples are random? Well, let's get into this today and let's find out. All right, so I didn't type up anything, so let's just read Doc Piper's notes. The president of an investment firm has observed that men and women have been hired in the following sequence. So man, 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 then one woman, then four men, man, 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 then 1, 2, 3 women, and then a man. It's a man, baby, yeah. At the 5% level of significance, test the personnel officer's claim that the sequence of men and women is random. Now notice, it says we're not testing for bias in favor of one gender or the other. There's definitely 8 men hired and 4 women, but we're testing only for the randomness in the way that the sequence has been made. Okay, so the test is based on order, not frequency. All right, so first and foremost, hypotheses. The 8 men and the 4 women have been hired in a random sequence versus H1. The sequence is not random. Now notice, there's absolutely zero equation for this. You know why? Because there is no mathematical equation that defines randomness. So there's no formula. So the verbals are everything. You need a verbal because that's the only thing you could do. Okay? The significance level is alpha 0.05. Good news. That's the only significance level. The test statistic is the G unit, all right, capital G. G represents the number of runs. What is a run? A run is just a sequence of data that exhibit the same characteristic. The sequence is either preceded by or followed by different data or no data at all. So let me go back up. How many runs are in this sequence right here? I'm going to go through with you. So there is 1 run right here. Then this 1 woman represents a second run. Make that a little bigger. These 4 men represent a third run. These 3 women represent a fourth run. And then this 1 man represents a fifth run. So if I did this correctly, G should be 5. That's it. Every time you change the variable, you have a new run. That's it. That's how you find G. So let me scroll back down. Okay. What are the assumptions? It is a sequence of 2 different characteristics, all right, men and women. The number of elements of the sequence that have one characteristic must be less than or equal to 20. And the number of elements in the second sequence that have the second characteristic must also be less than or equal to 20. So the natural question is, well, what if, Mr. Colodi, one of the variables is greater than 20? That's a great question. We're going to get to that in a minute. But for this particular hypothesis test, small sample, both are less than or equal to 20. The computation, straight up, we've done them already. N1 represents the number of men, there's 8 of them. N sub 2 represents the number of women, there's 4 of those. G represents the number of runs. We calculated that just a little while ago, it's 5. Now the decision rule. We're going to reject HO if G is greater than or equal to G with N1, comma, N2 at the alpha over 2 level. So N1 was 8 for the 8 men, N sub 2 is 4 for the 4 women, and then 0.025. Now it got cut off, so let's do this together. I'm going to go to the final table of the year. Holy moly guacamole, final table. Notice this says values of N1, values of N2. So N1 was 8, N sub 2 is 4, and if you cross-reference, I see this right here. There's a number just above the 8 and a number just below the 8. These are your decision rules right here. So let's go back to the test. We're going to reject HO if G is greater than or equal to G with these characteristics. So G is greater than 10. Or if G is less than or equal to 3. That's it. You just did your decision rule. Now, G was 5. Is 5 greater than or equal to 10 or less than or equal to 3? No, 5 is directly in between 3 and 10. So we're not going to reject HO. We are going to, and I'll do this theory in just a second, we are going to fail to reject HO. And we're going to say that the given, we're going to fail to reject HO that the given sequence of men and women is random. I want you to notice something right here. Even as a layman's term, I did not use the word except. Well, Piper also didn't use the word except anywhere in this verbal. We just failed to reject HO that the sequence is random. Not guilty, Your Honor. There's not enough evidence to prosecute. Okay. Now, what is the theory behind this runs test in general? What if the sequence looked like this? Man, 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 man. What if I only did 6? All right. In this particular case, G is going to equal 1 because it's all men. However, what if I did this? Man, woman, man, woman, man, woman. Again, 6 people were hired, and there's 1, 2, 3, 4, 5, 6. G equals 6 here. Oh my gosh, G. That's horrible. I should have done something different. G equals 6. That's a little better. Okay. The moral of the story is this. If you have too few runs, you're going to reject HO and say it's not really that random. If you have too many runs, you're also going to reject and say it's not random. Okay? That is the theory behind the runs test for randomness. Is it a perfect theory? No. It is not a perfect theory. But that is the theory behind the runs test. If there are too few runs, you reject. If there are too many runs, you reject. All right? If you're right in between. So is this test perfect? No. The first day that we began hypothesis testing, we talked about type 1 and 2 errors. Errors can be made. Let's look at example 2. A machine produces defective items D and acceptable items A in the following sequence. So you got 1 defective and then 4 acceptable. 1 defective, 4 acceptable. 1 defective, 4. There's an absolute pattern here. You guys can all see it like I can see it. This thing can't be random. So at the 5% level, test the claim that the sequence is random. So the first thing I'm going to do here is I'm going to look at this. There's 1, 2, 3, 4, 5, 6 defectives. And there's 4 times 6. There's 24 acceptable. Wait a second. Isn't 24 greater than 20? Yes. So we need a different hypothesis test. This is going to be a large sample test. So the hypotheses, sequence is random versus the sequence is not random. Okay. And so since the number of A's is greater than 20, this is beyond what we just did before. And so it's fitting what our test statistic is going to be. When the sample size is large enough, we always seem to go back to our friend Z. And how do you calculate Z? It's capital G. So we are actually still using G in the computation. Minus mu sub G divided by, that's a sigma. Can't read that. That's sigma sub G. Okay. Look at the assumptions now, different than before. Either N1 or N2 must be greater than 20. And it's a sequence of 2 different characteristics. So N1 represents the number of defectives, that was only 6. N sub 2 represents the number of acceptable, that's 24. G is the number of runs, and if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There are indeed 12 runs. Great. So if you know this number, you're 1/3 of the way to the Z-score. Mu sub G represents this entire thing right here. And notice I'm boxing the +1. People do this entire fraction, and then guess what they forget to do? The +1. And it's all just based on N. So 2 times N1 times N2 divided by N1 plus N2, and then get that fraction and then +1. Don't forget the +1. And you get the 10.6 right there. Sigma looks complex. It's not. It's honestly just a bunch of n's, n1, n2. So 2 times n sub 1 times n sub 2 times the entire term here, 2 times n sub 1 times n sub 2 minus n1 minus n2, close parentheses. All right, so that times that entire quantity divided by the quantity n1 plus n2 squared times the quantity n1 plus n2 minus 1. It's really not a big deal. You just got to plug and chug, work it all through. You get 1.69. That's the sigma. Then just put it all in. G minus mu sub g divided by sigma sub g, and you get 0.83. To finish this up, this is a 5% two-tailed z-score test. What's the decision rule? You know it. You love it. Reject if you get greater than 1.96 or less than negative 1.96. An easy decision rule here for the large sample. Is 0.83 greater than 1.96? It is not. So we are going to fail to reject HO that the sequence is random. And wait, time out. We're failing to reject HO. We're not rejecting and saying that this is not random. That's right. We're not rejecting this. And I'm pointing this out. This is a great example. I know he wrote good. I'm going to say great example of why we do not say except HO. Because this, I know it says examination reveals that this is a consistent pattern, which is clearly not random. However, our test at our level of significance could not pick up the pattern. What type of error did we just make? We failed to reject HO when it was clearly false. That's a type 2 error, everybody. We just committed a type 2 error. One more example, and holy moly, this year is done. All right, for the following set of data, you can also test for randomness above or below a certain number, like the mean or the median. So in this case, let's test for randomness above and below the mean using alpha 0.05. So the data is randomly distributed above and below the mean versus not randomly distributed above and below the mean. All right, let's do it. Alpha is 0.05. Now, first off, there's not even 20 total numbers here. So this is, we're going back to the small sample test from example 1. So it's the same assumptions and it's the same test statistic as example 1. Test statistic is G. The assumptions are the same as example 1. The first thing you'd need to compute if we're testing above and below the mean is the mean. Put them into L1, 1-bar stats. Then take the raw data and classify them in 2 ways. B for below the mean, A for above the mean. If it equals the mean, what if a number equals the mean, Mr. Clody? Then skip it. That number never existed. So keep it in the sequence that the problem gives you. So there's a bunch of B's here, then an A, then a B, and 2 A's, then a below, and then 3 A's, and a B and an A. So there's 8 B's, there's 7 A's, and there's 8 runs. Just like example 1. We're going to reject HO. If G is greater than or equal to G with 8 runs, then 7 runs. One more time, I'll go through this. I'm going to go down to 8, then across to 7, and I see it right here. So it's going to be less than or equal to 4 or greater than or equal to 13 if I didn't make any mistakes. All right, so greater than or equal to 13 or less than or equal to 4. Done. By the way, is 8 greater than or equal to 13 or less than or equal to 4? No, it's right in between. So we are going to fail to reject HO of the randomness above and below the mean. A couple notes and then we're done. We're going to delete anything from the sequence that equals the mean or the median. And it says you could also test for randomness above and below the median. For your homework, I give you one problem where you test above or below the median. That's it, folks. Congratulations. You've completed the course. Do this homework, do these homeworks, and we'll prepare for our final test. Good job, everybody. See you later.